Thanks so much for joining us today. Welcome to the Water Quality Protection Land Speaker Series. So we're happy to have you join us for, excuse me, one in this series of webinars. So I'm Audrey Stewart. I'm the volunteer coordinator or the conservation program coordinator for Austin Water's Wildland Conservation Division. The Wildland Conservation Division includes two programs, one which is the Balcones Canyonlands Preserve, which protects endangered species habitat in western Travis County. And this program, the Water Quality Protection Lands. The Water Quality Protection Lands safeguard groundwater in the Barton Springs segment of the Edwards Aquifer through the conservation and restoration of connected pieces of land in Hays and Travis counties. So by restoring native grassland savanna and healthy riparian ecosystems, the WQPL not only supplies high quality water to the aquifer, but it also provides habitat for wildlife, protects cultural resources and dark skies, and supports research to better understand the important resources protected by these lands. Today, we're really happy to have Lindsey Sydow. Lindsey's a senior hydrogeologist with the City of Austin's Watershed Protection Department, where she has had the joy of working as a self-proclaimed professional nerd since 2017. She holds a bachelor's degree in Environmental Geoscience from Texas A&M and a master's degree in Geological Sciences from the University of Texas.
Well, thanks, Audrey. Thanks, everyone else, for having me out. I'm really always excited to get to talk about this topic with people and help people really understand the special place that we all live and love. So, well, I'll go ahead and I guess she already introduced me, but yes, I'm Lindsey. I'm with the Aquifer Science and Conservation Group at the Watershed Protection Department, where I've been for about 6 years. And before I start my talk, I just want to acknowledge that I'm just like a tiny and more recent part of a long line of passionate scientists who've been working on groundwater tracing studies in Central Texas for over 25 years. Not only at the city, but also at the Barton Springs Edwards Aquifer Conservation District and local universities. And aside from my nod to David Byrne in the title here, I also want to give honorable mention to my former colleague, Saj Zapatello. When I started putting this talk together, I was remembering back, she headed up phase 15 of our dye tracing program, and she gave several talks where she made these really great slides and figures, and I wanted to borrow a bunch of them. So I borrowed several of her slides. So she's in here as well. I'm just making it off there. Okay, so let's get started. Water underground. Well, this is really what we're going to kind of, cover today. Water and geology in Austin. I'll just start talking about the brief overview. Groundwater tracing in general, how does it work? How does it work here? And, is this how most aquifers are studied? It is not. Why do we use dye tracers? I'm going to kind of cover a quick summary of past tracing studies, talk about the most recent chapter in our program, and then just kind of talk about generally, like, what is this program given us? Which I don't know that, too many people really appreciate, like, just how much the foundation of everything, not everything, but a lot of what we do in the Barton Springs Edwards Aquifer is based on the information we get from these studies. So I'll just start by showing you this poster. We at the Watershed Protection Department are fond of saying that Austin is a city of creeks, which you can see is very true on this map. These are Austin's watersheds. And water, in its most simplest, when you're thinking about it, flows downhill. And so this is, all the water that falls in this area, enters Shoal Creek and flows this way. So it's pretty simple to think about. It's just topography. Groundwater can follow similar rules, but it doesn't have to flow between these lines. So, the first thing I'll just kind of point out here is, down here in South Austin, which is mostly what we're going to be talking about today and talking about dye tracing in Barton Springs, these watersheds, mostly flow west to east. So just kind of something to keep in mind as we keep talking. So, we say we're a city of creeks, but we're also a city of springs. And I want to show this just to illustrate, this isn't even actually all the springs in Austin. That would be a much more crowded map. And even though I'm here to talk about dye tracing today and our karst springs, I like to remind people that we actually have over 1,000 documented springs in Austin. And, many of them are actual alluvial, here on the east side of town. And they're still important to our ecosystem and maintaining flowing creeks, which is maybe a small personal plug for a project I'm currently working on, looking at East Austin Springs too. So, but to look at, the setting of Austin, this is a geologic map of Austin from the Geologic Atlas of Texas. And at first glance, you can see there's a lot going on here. It's a pretty interesting place to be a geologist, actually. But to kind of show you what you're looking at, these greens over here are the Glen Rose and Edwards limestones that you know and love and hear about so much. And then all these lines through here are faults of the Balcones fault zone. And then over here, you have these reds and yellows that are alluvial deposits from former channels of the Colorado River as it kind of meandered around. And we even have a volcano down here, so it's a cool place to be a geologist. But one thing to think about is there's also groundwater in all of these places. And even though the talk is going to focus on studies we've done in the Edwards, I like to remind folks that we have lots of different types of groundwater systems here because, whoa, that was weird. Didn't mean to do that. Okay, sorry. We have lots of different types of groundwater systems here because we have lots of different geology. All right, so aquifers actually have a usability component to their definition, right? An aquifer transmits usable amounts of water to springs and wells. And like we just mentioned, there's lots of kinds: sand, gravel, rock, and karst. And one of the reasons I like to bring that up is, having grown up just down the road in San Marcos and hearing about the Edwards Aquifer all the time, I was really under the impression as a child that like all aquifers were like this, right? They're just big rivers underground is how I thought about it, back then. So I think it's important to know that most aquifers actually in the world are sand and gravel that's filled with water, and it moves much slower. We'll get into that a little bit, just to talk about the contrast of what's so special with the Edwards here. But the Edwards is a karst aquifer and formed by dissolution. So if you think back to your school classes and in science, you learned about physical and chemical weathering. Dissolution is chemical weathering. And, you dissolve out of the limestone these, sinkholes and caves, and it forms underground drainage systems. So this is a very simple way of how that chemical reaction happens. You have carbon dioxide that dissolves into the water. That happens in the air, but it also happens in the soil where there's a lot of carbon dioxide. And it forms this, weak acid, carbonic acid, that very slowly over a long period of time dissolves out these holes in the limestone. And if you have strong acid, you can squirt it on a piece of calcite here, and it makes that reaction go much faster, and you can actually see a bubble. So when you have all that dissolution happening in limestone, you end up with something like this. This is our basic karst aquifer. So there's a few things to point out here that I think are interesting. One reason I like this figure is that it shows the matrix and having water in it and the conduits. So, the conduits are, kind of the big, like, sexy thing we think of, right, when we're thinking about, oh, caves and sinkholes and all the cool stuff. But there is water in the formation as well. But the landscape, we think about here, we've got this recharge zone, right, where water infiltrates. And another fun thing about this figure is it shows the dookie brown arrows from the septic system going into the groundwater system, and there's a car in this sinkhole over here. So nod to the Water Quality Protection Lands program. Clean water comes from clean land, and really, they maybe don't have the cleanest land happening here. They really need some water quality protection lands. I think that's really everything I want to talk about here. Oh, I guess one thing is, when we think about like what dye tracing has taught us about the Edwards Aquifer, one thing to take away from this figure is, the conduit system, like, it's very obvious to us looking at this, but it's not actually like most of the underground, right? So the well that you drill here, like this one's not hitting a conduit. And wells are how we observe what's happening in an aquifer in most of the world. Because in most of the world, right, when you've got these sand and gravel aquifers, you can't crawl inside them like you can in a cave in the Edwards Aquifer. You can't get that like visual of what's happening. You look at, well levels and you do testing on those wells. So you could get like a misconception about what's happening in the aquifer from if a majority of your wells are like this one and they don't hit these big passages. Okay, so that's a generic karst aquifer. This is our karst aquifer, the one we know and love. The Edwards Aquifer, the whole thing actually takes up a lot of, South and Central Texas here. And our segment here that we study at the City of Austin is the Barton Springs segment. And, out here, contributing zone, it's in the news a lot lately, right? Like Jacob's Well is dry. This is, really the Trinity Aquifer out here. But for the purposes of thinking about the Edwards Aquifer, the creeks that, the rain that falls out here and flows into creeks that eventually flow across the recharge zone, this is contributing to the Edwards Aquifer. So that's why it's called the contributing zone, even though it is also its own aquifer. So, this is kind of the map view of what's going on. You have those, remember from the watershed map, you've got like 6 watersheds flowing this way across here. And then this is the cross-section view of what we have going on here. And one thing I think is interesting is you really see that the fault zone provides more, ability for water to infiltrate into the aquifer. But what you've got going on here is, groundwater in the higher, plateau area becoming surface water, becoming groundwater, becoming surface water again. So that's, right now we're having so many issues with water. It's important to know that that's how it works. Also important to know that when you have recharge entering these holes, there's little to no filtration, right? So the water coming in here, it's basically entering a rock pipe, and it's part of why we have all of those signs. If you drive onto the recharge zone that say now entering the recharge zone. And so, we know the water discharges at Barton Springs. You can actually see kind of the main fault over here. This is where we sample when we're collecting samples. The big cave that has the USGS instruments that measure every 15 minutes is down over here below the diving board. But for our hand samples, we don't dive down there. We just go over here to the fault. In case you didn't know, that was where water comes out as well. And in addition to it being our favorite swimming hole, it's also these guys' favorite swimming holes. We have 2 endangered salamanders, the Barton Springs salamander and the Austin blind salamander that live in the pool and Eliza Spring and the aquifer in that area. So with the drought going on and talking about, surface water becoming groundwater, becoming surface water again, I always think it's interesting to note, Texas's rule of capture with regard to how we regulate groundwater. Essentially, if you can pump it, you can have it, except for, there are groundwater conservation districts that we have that try to, limit and track that. But, the rule in 1904 decided that, groundwater is so secret, occult, and concealed that attempts to regulate it are basically impossible. But this guy is in the groundwater right now, so it's not that secret. Like, it's there. We can study it. And spoiler alert, it's all the same water. We saw the surface water becomes the groundwater, and regulating them differently is maybe not always the best for the resource. So now we're going to talk about actually the design and the meat of doing a groundwater tracing study. At its heart, it's actually pretty simple. Now, you have to do calculations and planning and all that, but really, what you put in comes out. This is a cripple crawfish cave. It's on water quality protection lands. Put dye in, hope that it comes out at Barton Springs, or this is Upper Barton Spring in the Greenbelt, just upstream of Barton Creek of Barton Springs Pool. So when you do a dye tracing study, you're basically wanting to put non-toxic fluorescent dye. Yes, non-toxic. We are not in the business of hurting anyone. This dye is used in the food and drug industries. It's very safe. No endangered species are at risk of anything when this stuff is used. But you want to make sure that you put it down, whatever your sinkhole or cave feature is, with enough flush water for it to reach the water table so that it can, trace the water down in the saturated zone. And this is, what that looks like when you're injecting it. You have bright, fun colors and flush water going in, and it's always kind of exciting if it's this is not a new feature, I don't believe, that was traced, but when you've got a new feature that you're tracing, it's always exciting when you see how much water it can take, right? Does it back up any, or does it really flow? That's the water nerd in me talking. We're like, oh, that one's really taking water. It's kind of fun. So if you've done your job right, what you see at the springs when it comes out is nothing. The tracer is there, and when it's run through equipment that can detect the fluorescence of the dye, you will see it in this data, but you will not have alarmed anybody at Austin's Crown Jewel swimming hole that there may have been some sort of toxic problem. So there's a few ways that we analyze for dye at the receptor sites. The first one here is water samples. So when you take a water sample, you're looking at a moment in time, like what's in that little bit of water that you pulled out. And up here, we've got my friend Yaz is working on a auto sampler, which can pull out several samples over a course of time. So, the tired but excited scientist isn't sitting there like collecting samples all night long. They can go take a break and then come back and put new bottles in. The other way that we analyze for dye is with these charcoal packets, and the way they work is dye adsorbs onto the charcoal, and then the packet is analyzed. What this can do, separate from, this is a moment in time, this is left out for a period of time. So if for some reason you don't have an auto sampler, so you're only collecting samples when you can be there, or the time series on this is just set for whatever reason, it messes up that you miss your breakthrough curve coming through. This dye packet will tell you, like, okay, well, maybe you missed the pretty curve you were hoping to see, but the dye was here. It happened. There's a connection. The other useful thing about these charcoal packets is it can actually save you money. You can put one of these out for like a week, and you can run it at the lab first, right? And if there's no dye on this, you don't need to run 50 water samples to see if there's a breakthrough curve, because there was none on the packet. So just an interesting tidbit. So after you analyze for the dye, you hopefully end up with something like this. This is some data from our trace that was done in 2017. And this dashed line means that there was an, to put it nicely, interested party at the pool who thought the tubing looked curious and actually pulled it out of the fault there in that photo I showed you before. So the first part of this breakthrough curve, we don't know if it came through like here or here, but altogether, it's not a huge chunk of time missing. So this is still really good data. Let's see here. All right, so why do we do tracing in the first place? Like, okay, playing with colors and, quote, having to spend a lot of time at Barton Springs sounds great, but why are we doing this? Is this how you study all aquifers? And the answer is no. The reason we're doing this is because traditional aquifer testing methods don't work very well in karst. And what I mean by that is, when I said most aquifers aren't karst, when you're a baby hydrogeologist and you take your first hydrogeology class, unless you're at a university that's like near one of these karst aquifers, you're probably not really learning much about at least these karst methods. You're learning the methods that get used most places in these sand and gravel aquifers. And those tests are designed for groundwater velocities several orders of magnitude smaller than what we have in these cave and conduit systems. So this is just an example of one of those kinds of tests. This is called a slug test. And if you picture that everything around this is sand and gravel, water moves relatively slowly. So that you drop this slug in, it raises the water level or the head, and then you measure the amount of time it takes for this to go back to the static level. And then you can do the same thing when you pull the slug out, you measure the amount of time it takes for the water level to recover up to here. And you do some fancy math on that data, and you get groundwater velocities that are on the order of 0.0001 centimeters per second, whereas the velocities we're dealing with are 10 centimeters per second. That's in some cases over 5 miles a day. So, if you picture that you've got, a conduit in your well down here, and you drop this slug in, like this water level is going to recover so fast, you're going to have really meaningless data from this if you're trying to test a karst aquifer. So just to kind of illustrate that point a little more, this is like what you would get if you're looking at a sand aquifer, right? We'd measure the levels, and all these little black dots are wells. We'd measure the levels, and we'd create what looks like a topographic map, but it's really of water levels. I mean, you can think of it like a water topographic map. And you draw lines across those lines to figure out where the water's flowing. In this case, this is a well field, so the water flows towards the wells because it lowers the level in that area. But, for our purposes, this is what we end up with, right? And, why are we doing tracers? Like I said, at its heart, it's simple-ish. We'll talk about the ish, in a little bit. But at its heart, it's simple. You put something in, you measure where it comes out, you look at, the dispersion of what you put in, you look at the travel time, you can figure out a lot of things by doing this. And really, it's also the best smoking gun for proving connectivity of different areas. And we'll kind of come back to that point a few times here. But, you can kind of see we've got a few groundwater basins mapped here. And the way that those were determined, right, is by putting dye in here. And okay, dye you put in here doesn't come out at Barton Springs. It comes out at Cold Spring. The dye you put in here comes out at Upper Spring, but this dye doesn't come out at Upper Spring. So, thinking about that watershed map earlier, you can kind of think about these as like spring sheds. And, the lines, like we said, they don't necessarily run the same way as the watershed lines do. And just, for fun, really is the best smoking gun for proving connectivity. This is what no hydrogeologist really wants to see, or at least it's not the call they want to get, right? With, hey, all my laundry is pink, or my bathtub I've been scrubbing it for a while and feels ruined. This is from a trace that was done in Upper Onion Creek out near Driftwood several years back. And this was a well at a home nearby to where the injection happened. And, part of the interest for that study was, okay, well, there was a permit being sought to discharge treated wastewater. It's not like direct poop water, right? But treated wastewater to Onion Creek. And, there's concern about well, does that recharge? How connected is it? And I mean, this house nearby is obviously very connected to what happens in Onion Creek, right? So you can't deny a pink bathtub. So something else that we should mention here is tracers are not always fluorescent dyes. Those are, the intentional ones that we use because they're, we know they're non-toxic, and we know how the analysis and everything goes with them. But there are other things that you can trace. Really, anything you can measure at a spring, if you can, kind of determine a source, you can use as a tracer, even if you're not using it as something you injected. So just to kind of explain what's going on here, this is really us tracing storm flow at Barton Springs. This is a chemograph looking at specific conductance is this blue line. Okay, so specific conductance, also called conductivity, is really just a measure of how electrically conductive the water is due to minerals and salts and things dissolved in it. So water that's in contact with rock, like water in the aquifer, is going to have, clearly before the storm, right, this was its conductivity. But then water that is rain, right, it comes from the sky, it hasn't been in contact with the rock, it doesn't have a bunch of stuff dissolved in it at all. So it kind of dilutes that signature, and you see the conductivity drop as the rain comes through, and then, it slowly recovers. Oh, and then we've got this other little dip over here. We're kind of thinking, yeah, that could be from Onion Creek as it comes in from further out, but we haven't done a trace to totally verify that. We're pretty sure that's what that is. But another tracer we have on here is turbidity. So when you have a storm, we always think about the runoff, and floodwaters can be really cloudy, right? So here, this initial first flush after the rain comes through, we have a turbidity spike. And I know there's a little bit more here, but you can really see how that matches up with the influx of the rainwater. It's also the influx of the sediment. And tracers also don't have to be natural or intentional. This picture might look a little familiar to some of y'all. About 5 years ago, you might remember there was this kind of big hullabaloo when it was like maybe a week before Christmas, and Barton Springs turned white at lunchtime in the middle of the day. And the pool had to close because we didn't know what it was. It was just sediment or this substance that's filling the pool, and we don't know if it's safe. It was eventually traced to some wells being drilled a few miles away in the neighborhood for a geothermal system. And they just, happened to hit a conduit, and a lot of the stuff they were putting down their wells showed up at the springs. But, we were able to use, those natural tracers I just showed you to kind of solve the mystery a little bit, right? There was some speculation actually at the time, since it was white, the sediment that came through right here, actually. There was some speculation that, it rained a couple of days ago, and there's a big construction site down south. I bet it came from there. And, we're able to look at this graph and see that, conductivity didn't drop like it does when it rains. So we're very confident this is not rain runoff from a construction site. Because here's, there was a storm just like a week later, and we see how it responded. And look at the turbidity from that storm relative to these wells, because they were such a discrete pumping in of sediment. And in this case, it's the bentonite grout that you use to fill the annular space of a well. So, and the other thing about these was they're really sharp, right? So we can see that they probably came from reasonably close by in the watershed, because they're not having time to disperse like this sediment that's coming from storm runoff from all over the recharge and contributing zone. So now I'm just going to kind of go through the history here of the traces that have been done. I'm certainly not going to talk in depth about all of these, because that would take a really long time, but I'd just like to kind of show you kind of the evolution of how these traces have gone. So the first ones in the mid-90s are very close to the springs in Barton Creek. They came out at Cold Springs. And you start moving further out, Williamson Creek watershed, Slaughter Creek watershed, Bear and Little Bear. Finally here in 2000, they did some injections in Onion Creek. And then, this was, discharge is higher here, right? This is high dish at Barton Springs, but this travel time here, 3.5 days, that was pretty cool and surprising. And one thing I want to point out, I guess, before we start getting into it here, is we know that this groundwater divide moves, and we're going to talk about how tracing told us that too. So here it's 2005, it's still high discharge at Barton Springs. And, an injection done at Onion Creek, it shows up at Barton Springs as expected, but it also showed up at San Marcos Springs. And this is under high flow conditions. Okay, so, a couple years go by, and then an injection's done here in the Blanco River at low flow, not as low as right now, because we're really hurting, but low flow. So injection done in the Blanco River watershed to the south that we normally think of as going to San Marcos Springs, it also shows up at Barton Springs. So you get this idea that the groundwater divide here moves based on changing conditions. And then this is that trace I showed you all the pictures and video of that was done in 2017. So, you put all of that together, and what you end up with is this map. I know I already showed it to you earlier, but it's really cool. This is our, current understanding of how groundwater flows in the aquifer. So now I'm going to take just a few minutes to talk to you about our most recent trace. I don't know if it was our finest hour, but we did learn some good stuff from it. So we'll talk about it here anyway. So it happened in March 2022. Yeah, like I said up here, it puts the ish in simple-ish. One thing we were really excited to do was deploy an auto sampler at Cold Spring. That had not been done before. And you've been out on the lake, it gets crowded. There's always concern about tampering out there. But since this was March and it was still reasonably cool, we figured not a lot of people out there. The people are, regular paddlers who are out there. It's not the party flotilla that takes over from like May to September. They were still in hibernation. So we were like, okay, we'll lock the auto sampler up and we'll put a sign on it that says, "This is science, call us for more information. Please don't mess with this," and hope for the best. And it actually went well. We didn't have any issues. We had planned 3 injections around the boundaries with like the Sunset Valley and Cold Springs basins, but we were only able to do 2. And just to talk about that a little bit, these are the 2 injections that we were able to do: Harbor Park Sink and Gaines Southwest Parkway Cave. I'll talk about those in just a minute. The other injection point we wanted to do, and just, to like paint the picture for you, it was this really nice pool, like just downstream of Airman's Cave. We went out on like Sunday night to scope out for our injection, because since we were doing it in the creek a long way from a road, we weren't really able to get flush water down. So we needed the creek to do the flushing for us. And there's a spot where the pool is like disappearing into the creek bed in like a discrete location. And we're like, yes, this is perfect. This injection is going to be amazing. So, the day of the injection comes, literally, I think it was 2 days later. We do this injection at Gaines Southwest Parkway. We do this injection at Harbor Park Sink. It's the end of the day. We're hiking the Greenbelt to get down here at like dark. And we get there and the creek is dried up like 500 yards past that. I'm like, in 2 days this happened? Really? But that's what happened, and it was stretched out over a really long distance, and the flow wasn't adequate. It was like kind of just in the gravel. It wasn't a good place to do an injection, so we didn't end up getting to do this one. Some other things to point out on this figure, just before I move on, the receptor sites are all here in red. And these 2 wells I'll end up talking about a little bit later. So these are a couple of Edwards wells that we monitored. Okay, so we didn't get to do our 1 injection, but these are the injections we did get to do. Harper Park Sink is an upland sinkhole, and it's one that was actually found, when a neighborhood was coming in to be developed. That's actually how a lot of these features, at least in the city proper, get found. When you're checking for development to make sure nobody's going to like build their resort on top of a sinkhole. So this one was identified. It's fenced off and protected to keep street runoff and that kind of thing out of it. And so this injection was done here. It was one of those moments where we were all really excited about how much water it took, because not being in a creek bed or something and not getting a lot of constant flushing, you're not really sure what the capacity of it is, but it never even backed up. It was a really cool feature. And the other feature was really cool too. This is at Gaines Southwest Parkway Cave. It's in Gaines Creek, right next to Southwest Parkway. And there's actually, a series of faults kind of running through the creek right here that I gotta say, some rogue caver clearly had been in here, like excavating all of them, hoping they would find a place where they opened up. None of them do. So, you get down there and there's like the little small holes that we injected into, and there's nothing else. But the first time we were out there, actually because there was issues with this pond, which I'll talk about in a second, we were like, whoa, someone has done a lot of work here. It's a really, really interesting spot. So, yeah, but like I was saying, this pond is the other thing that's interesting about this feature. It's, in the creek bed, and this pond is right next to it, the stormwater pond. So when I say right next to it, I mean, this photo is taken from like the edge of the creek bank, up a little bluff, and then the fence is right there. And this pond actually drains into the creek and kind of into these sinkholes, which becomes important in a little bit. So we do the injections, and we were expecting the dye to show up at Cold Springs with our auto sampler there in like 3 days. And 3 days goes by, nothing. 5, nothing. We get to a week. We're all kind of like hitting our heads a little bit, like, I bet we didn't use enough flush water. No. And, we talked to the lab, and they kind of suggested, well, if you put more flush water down now, you're going to mess with your study. Just wait. And we're like, I think our study is already messed with. Maybe we should do it. But so this is, when you're doing monitoring for a dye trace, you're going out every day to change the packets on the weekends. And so we're doing all this work every day. We're kind of stressed out. We're not seeing any dye. And that's the sort of the setting that happened when I was looking through my phone, trying to, find a couple extra pictures for this presentation, and came across these, which I had totally forgotten that I was like really pregnant during this study. And now realizing, seeing this happy face here, going out in all these stressful conditions. This was a freak cold snap. We're like paddling up whitecaps on the lake. It was like 38 degrees. And I'm just thinking about my poor coworkers and being like, wow, my perspective now is different than it was then. I really thought I was helping, but like, I don't know that I was being all that helpful out here. Anyway, I just thought I'd throw it up there because it was really hilarious to me. I'd completely forgotten about that aspect of this study. So, we do get lucky. After about 3 weeks, it rains, and the rain, flushes water down Gaines Creek and fills that pond, which also flows into Gaines Creek, and, does what our inadequate amount of flush water couldn't, and flushes the rest of the dye through. And so we get a detection here, the first one 56 hours after that storm event, which is more on the order of what we were expecting to see. So, 1.75 miles per day. This was at moderate flow conditions, around 50 some odd CFS at Barton Springs. So, we're relieved we got some result, but we're just all kind of feeling like, okay, this did not go as planned. But one thing that this study really did do was give us some confidence that we could do a storm trace at some point in the future. And the exciting thing about that is, I showed you that graph of storm flow coming in at Barton Springs, the orange and blue lines with the turbidity and the conductivity. There are lots of little drops and humps in that graph, and we've wanted for a while, since we started looking into that more, to be able to tie those to, like that came from this creek at this time with a dye trace. But the logistics of doing a storm trace could be tricky, right? Like you have to put the dye in presumably to a dry creek bed so that it gets flushed in exactly with the rainwater. And you don't want it degraded in the sun, and you have to be really confident about the forecast that it's going to be, enough rain, and that you have a creek bed that's dry instead of flowing. So it's going to require some specific conditions, but this accidental storm trace we did, kind of told us that, okay, maybe we could do it. Maybe it's not as hard as we're thinking. So, now we're going to talk about what tracing has really given us, like as a program, but also, as scientists and just as, community members in the city of Austin. So what you're looking at here, remember those 2 wells I showed you on the map saying that we monitored them in our most recent trace. This is the water levels in those wells over the course of this study. Now, over the course of this dye trace, discharge was dropping at Barton Springs. I think it went from 60 to 50 or something in the span of time that we were monitoring. Well, what you see here is this well is dropping too. It's dropping, just keeping in time pretty much exactly with what's happening at Barton Springs. But this well is staying pretty static. And if you remember back to that, first kind of karst illustration I showed you, we talked about the wells don't always hit the conduits, right? This is a really good example of this is a well that has communication with the conduits. And this well is really just in the matrix. So when we think about what tracing has given us, I want you to think back to a previous time, 40 years ago. It's before we were really doing tracing, and you're like a groundwater manager here in Austin or anywhere really along the Edwards Aquifer. And, you have an aquifer, it's heterogeneous because you have wells like this, right? You have wells, one well behaves like this, one well behaves like this, and they're not that far from each other. There's not like good reasons other than just the really heterogeneous aquifer to explain this. And you have creeks and rivers along the fault zone that lose water. And there's springs that just pump out a lot of water, but like that's the information you have. So from looking at this, if you're trying to use traditional aquifer testing methods and you're like, okay, well, maybe we'll put together what we get from this well and we'll come up with some average number. Really what you end up with is the old idea we had, which is that, they used to think it took years for water to reach these springs from where it went in. Tracing is really the main reason we have the mental model we have now to know that, the water is moving on the orders of miles per day and not like feet per year, like a lot of aquifers do. And part of the reason I say that is I really want to highlight how relatively modern, this understanding is, because I have distinct memory of being a child. Like I said, I grew up in San Marcos, riding the glass bottom boats, shout out to Ralph the Swimming Pig here, and being told that, the reason the water here is so clear is because it takes years for it to get here and it filters through the crystalline limestone, and that, that filtration and years of travel makes it this beautiful, clean water. But, now, again, like I said, this is a water quality protection land stock. Now we know the reason the water is clear is because clean water comes from clean land, and we have to keep that land clean and take care of it. And, conversely to that, I was talking to Scott Hires, my supervisor yesterday, and we were, talking about this talk, and he reminded me about the neighborhoods that I do some work in South Austin that were built, I think 70s-ish, 60s, that time period. They were, because of our previous, thoughts about the aquifer and that water that goes in takes years to get to the springs and it's highly filtered. There are neighborhoods that were engineered for their stormwater to go to the sinkholes. Like, it doesn't go to storm drains that then go to creeks. There are like pipes that go to sinkholes on purpose, because at that time they thought, oh, well, this is going to do a better job filtering this water than anything we could do. And, now we know better. And I know, water quality protection lands, I know y'all have seen this map probably a lot of times, but in thinking again about what tracing has given us, those early traces, being that smoking gun showing connectivity, really galvanized the water quality protection lands program. And, we knew that there was like losses in these creeks, but, combining that information with tracing gave us a lot more info, and some work that, Nico Howard did actually estimated that like 33% of Barton Springs flow actually originates down here in Onion Creek, which, without that information, you would probably make the assumption a lot of people used to, right, that most of it would come from Barton Creek. So, this work really also kind of told us like where to buy land to be the most effective at helping protect Barton Springs. Another thing it has given us, it informs basically the way we manage this resource, right? So one thing that we do to manage this resource is we have a catastrophic spill plan for the recharging contributing zones. Now we have to have a habitat conservation plan for the Barton Springs and Austin blind salamanders to be able to operate Barton Springs as a public pool, because it's an endangered species habitat, right? Like, it's open to the public. We have to have a plan to manage that habitat. And the catastrophic spill plan is part of that. So, we have this map that tells you like, okay, relative travel times from different areas, and, the work that was done to delineate the different basins. I mean, that's really the difference, if there's a spill, between knowing where to put your efforts, right? Like, if the spill is over here, then what you're doing is trying to, get water to the captive breeding facility and then shut off the well so you don't poison all the salamanders there. But if the spill is over here, then okay, maybe we want to go try and rescue some salamanders from Eliza Spring. And, we'll keep an eye on the well at the captive breeding facility, but it might be okay. We just have to, this is provided that knowledge base for us. And then, one more thing, just because this is a very exciting thing that's about to be happening, is tracing has given us, justification for engineering solutions. This is Stoneledge Quarry, and it was purchased by Water Quality Protection Land several years ago. Back when it was mined, they hit the water table. This is it. This is the Edwards Aquifer right here. It's a perennial pond because it's the water table. And we've known for years that it was the aquifer because it matches the level in a nearby Edwards well. So in 2017, what you're looking at here is that they also traced this feature as part of that study. And the idea here is a really cool engineering project that we'll talk about. And so just to kind of show here, this is that well I was mentioning, that the level matches the level in the pond. The other unique thing about, other than this being an abandoned quarry with the exposed Edwards Aquifer, is that Little Bear Creek flows right next to it. So, this proposed project is to cut a channel that will divert high flows, only high flows. It doesn't take all the creek out of Little Bear Creek. It just takes excess flows, and put it into the quarry where it can slowly infiltrate and recharge the aquifer. And it's really exciting, cutting edge thing, and it goes to council next week. So very, very exciting. So, what's next for tracing in Austin? This talk was, mostly about what's been done in the Barton Springs segment, especially given that it's water quality protection lands talk, and that's all the water quality protection lands. But we're starting to put an eye toward doing maybe some more traces in the northern segment. There have been some traces up there, but they haven't been nearly so successful at really figuring out the system. And we'd like to do more there. This picture is from a icy field day several years back. I mean, you can see water still comes through the Edwards and makes itself known in the north as well. And then, like I mentioned before, we'd also like to do a storm trace at some point once we can make that happen. So just to, kind of hammer home the take-home points. I know I literally said most of this, but just to kind of make it clear, tracing is really the foundation for a lot of the work that's been done that led to our current understanding of how the aquifer works, and just how heterogeneous the conditions are, and just how fast the flow velocities are. It's also a foundation for establishing the Water Quality Protection Lands program and the catastrophic spill response plan. Remember, tracers can be anything. They can be naturally occurring substances. They can be unintentional. That grouting of the pool was unfortunate, but it was interesting. I gotta say, it was its own little tracer test. And just remember, it's all the same water. Surface water becomes groundwater, becomes surface water again. And it's important that, as scientists at least, that we think of it that way. And finally, it's informing our efforts to protect and manage recharge, especially really awesome projects like this. This is what Stoneledge looked like when it had all that dye in it. So that's the end of my talk. I guess we can do questions now.
Thank you so much, Lindsey. This is just a fascinating talk, and I have my own questions, but I won't be greedy. I'm going to start with everybody else's questions. So if you have more questions, pop them in the chat. We'll get started with Evan's question. So have any dye tracing studies been conducted at the limestone springs along Walnut Creek east of I-35, or more generally, anything you can share about work studying East Austin Springs and insights and surprises from any of that work?
Yes, I can talk about that a little bit. We've not done any traces there along Walnut Creek. That area is not really, quite the same as far as discrete recharge features. You're not looking at oh, here's a sinkhole that we definitely know what's going to happen here with this. As far as the East Austin Springs project goes, we're mostly focused on the alluvial springs right now, and not to dive too deep into the plan for that, but basically what we're trying to do is we're starting by just characterizing like geochemically what those look like, because we have just tons of data on these karst aquifers and mainly Barton Springs. And when we go out to, for example, test water, if we get a call that's like, is this a leak or is it a spring or, whatever, we have this idea and this like range we've calculated of different parameters that are what we think groundwater is, but it's not necessarily the case. We're geologists, we know the rocks influence the chemistry of the water, right? So we are seeing that the chemistry is a little different in these alluvial aquifers on the east side, and it's just good for us to have knowledge about all of it. So, and we are seeing that some springs are kind of impacted and some are not, and it's good to be able to characterize that too.
Great. Okay, so David asked, so Lindsey, if it takes water only a few days to reach Barton Springs, it hasn't rained in weeks, why do the springs still have water coming out of them? Is it all from the Blanco River?
No. And to be honest, I don't actually know if the Blanco River is even flowing all the way to the recharge zone right now. Someone else may. I am as you all saw in my talk from like a year and a half ago, I was pregnant. I have a little toddler right now. I haven't been down to the Blanco River in a while. So I don't know where it is right now, but most of that water is like coming from storage, right? And we can see that. Remember we talked about the specific conductivity and that water in contact with rock has more minerals and salts dissolved in it. Right now that conductivity number is quite a bit higher than what I showed you on that graph from, I think it was like 4 years ago. And that's because that's water that's been in storage longer. It hasn't rained in 5 months. We're not getting water that has only been in there for 4 months, right? It's water that's been in storage for a while. So.
Interesting. So on a related note to Evan's question, Evan says, thanks for your response. Is it, so say someone sees what they think is a sensitive karst area or karst area and a spill, or think there's something going into it. I know you mentioned some of the work Watershed does is to protect sensitive karst features around areas that have, contaminants from roads or anything. Is there a number people can report potential issues to, or like,
yes,
what would that be?
I should have it memorized.
Sorry.
Anybody else listening might have it memorized. It's the last 4 numbers are like 2550. Hold on, I can find it.
That's okay. While we wait, I can also look it up and pop it in the chat. That was just,
yeah, let me here, I'll do this real quick.
Oh, David's got it. 974-2550. I'm going to put that in. So this is like, if anyone, it's like a spill report hotline. Is that kind of what you would call?
Yeah. So it's available 24 hours a day to call. Somebody is always there to answer it and respond to a spill. And thanks, David, for putting that. I couldn't remember the 974.
Okay, great.
550.
Okay. Barbara has a question. You mentioned a proposal, that the quarry proposal that was going to be sent to council next week. If they approve it, is this something citizens will vote on, or how does that process work?
Ooh, so no, it's not something that citizens vote on. There's been, like a comment period and all of that prior to now. But there's been years of work have been going into securing all the appropriate permits and doing the design to make sure that there will be no harmful outcomes from any alterations to any of this. So if you're interested to hear about it, you can listen in, but it's not a voting thing.
Great. And on a related note, I just put up some links. One of them is to join a guided hike. And we actually have a guided hike planned for that site on October 8th. called New Life for an Old Quarry that's going to talk about, this is the Water Quality Protection Land's first recharge enhancement project. So if you're interested in it, that's going to be a great one to attend. So I put that link up there along with some others.
Yeah. And one thing to think, one cool way to think about that, right, is like, it's a big open hole into the aquifer. If it hadn't been bought by Water Quality Protection Lands, it really kind of represents this big like spill and contamination risk, right? So it's being repurposed to take, something that was not great and trying to make lemonade, so to speak. So
yeah. Thanks. Okay, so Sarah's got a question also regarding the quarry. It's very exciting in that big like green. It's very eye-catching when you look at those dye trace studies. Regarding the quarry engineering project, is there concern about losing more water to evaporation in a large pool versus keeping it in the creek?
Not really, because, and I know David and Scott worked on this a lot. So if I don't like cover everything, feel free to pipe in with some questions. But realistically, when the water is going down Little Bear Creek, it's going to cross the recharge zone pretty quickly, and then it will enter Onion Creek and go to the Colorado River, where it's going to be exposed to the surface down there anyway. But here, it's going to be held over the recharge zone where it has more opportunity to recharge the aquifer. So it's, it's really just changing where it goes. Great.
And I have a back to school question for you. So, I mean, in honor of back to school, you have a really cool job. And, prior to this job researching and protecting Austin's groundwater resources, you were an environmental consultant, mostly working in planning and executing contaminated site evaluations. And I'm just curious how you got interested in your career, what tips you'd give to any young folks who think this sounds like a cool thing to do.
Oh, that is a good question. Well, I showed y'all some pictures from San Marcos Springs. I mean, realistically, I got interested in it right by living there and swimming in the river all the time. And I mean, glass bottom boat is like, I don't know, it left a good impression on me. So I think just, exposure to, there's this quote, I don't remember who it's by, but it's like, we only protect the things we love and we can only love the things we know about. And it's kind of attributed to, that Glen Canyon dam, that Glen Canyon was dammed up because nobody knew about it. So I think really just like going to these places and experiencing the magic of them is really a big part of like inspiring, wanting to do that work. And then just, science classes in school. I mean, if you engage with them, they engage with you, and it's fun. So
yeah, go school. Well, great. Thank you so much, Lindsey. This is just so fascinating, and we'll end it here because it's 1 o'clock. But yeah, really appreciate you taking the time to share this kind of history and science of dye tracing. It's really fascinating. Thanks for the work you do.
Great. Thank you.
All right. Thanks everyone for joining us. You can find that recording in that link, and we'll hope to see you next time. Take care.